Hey everybody, it's Wednesday, December 9th, and as you can see here in the aim today, our goal for this video is going to be all about how Newton's laws, and specifically Kepler's laws, describe planetary motion. As I mentioned in the video yesterday, Kepler's laws of planetary motion are not explicitly in this course. However, it is highly suggested by the people who designed the course that we mention these ideas specifically because it sort of fosters a lot of connections between a wide variety of these problems. I'm going to take some time to talk about it here at this point in the course because I think it'll be a good time to introduce it because, as I also mentioned yesterday, because it connects so many things, it can come up again and again and again. I also think it's probably important to mention, just for your own peace of mind, perhaps, that we are in good shape as far as like the pacing and the schedule is concerned. The next topic that I have to start is circular motion, and that I started last year on December 17th. So we're in pretty good shape. We're going to take the test at the end of this week, and we should start circular motion the latest on Monday, which is the 14th. And so we're in good shape as far as the schedule is concerned. And so we can take a couple days to discuss this because not only are they relatively important ideas for the course, they're also important ideas for physics. And so I think it's good to be able to understand these because, like learning is fun, right? So the main goal for today is to talk about Kepler's laws of planetary motion. And to talk about Kepler's laws of planetary motion, we first have to start the story shortly before Kepler's time. So our story begins with a man named Tycho Brahe. Obviously, as you can tell, fantastic mustache. So Tycho Brahe was an astronomer in, as you can see here, the late 1500s. And it is pretty widely agreed upon that he was one of the most prominent astronomers of the day. It's really important, I think, for us in modern society with computers and cell phones to think about how like basic, not only just like how basic everyday tasks were accomplished, but how something like astronomy would be accomplished by somebody with the primitive tools that they had in the late 1500s. Even just organizing the data from astronomical observations was like a pretty big task compared to the things that we have to do today. Like you've seen already in the lab work that we've done, we just take numbers and throw them in an Excel spreadsheet and get it to make graphs for us. Every time these people had to make graphs, they had to plot them by hand. Every time, these people had to organize data, they had to copy it down all by hand and preserve it and put it in a proper order after the fact. And so this stuff is pretty complicated. And Tycho Brahe was a gifted astronomer. He made good observations of various astronomical phenomenon, the position and location of stars, and started to track how they were moving. And because taking this kind of data is such laborious work, he was very protective of his data. He wouldn't really let anybody take a close look at it. And one day, he hired a lab assistant named Johannes Kepler, and Kepler impressed him. He had interesting ideas. He also was really diligent in the lab and was really committed to getting good data and helping Brahe organize his data. And so Brahe started to give him more and more access over time to the data that he was collecting. Now, Kepler, around the early 1600s, late 1500s, early 1600s, started to get some ideas of his own about how planets moved. And he really wanted to test his ideas out by looking at the motion of Mars, which Brahe was really closely tracking by 1600, 1601. And Kepler knew that he basically wasn't going to be able to just like steal Brahe's data and use it for his own. And so he had a little bit of a problem because he knew that the quality of Brahe's data would enable him to make these great, confirmation or essentially to refute his own ideas. But, he had a little bit of a problem because he couldn't just steal his data, and he was working so much in Brahe's lab that it presented a little bit of a problem. In a strange turn of events, and probably what is one of the weirder stories in science, Tycho Brahe is at a banquet, a dinner of the day, and he has to go to the bathroom. And etiquette in that time dictates that you should not just get up from a table when you're sitting there, because that's rude somehow. And so he decides, like, you know what? Let me hold it. I'll wait until this dinner is over. And it's important to realize banquets in that day, like, these people had nothing to do. They weren't going to like go home and watch Netflix or something. This was all they did. So they were there for hours and hours and hours. And he's got to pee really bad. And he doesn't. And so he holds it and holds it and holds it. And by the time the banquet is over, he can't go. And eventually his bladder bursts and he dies. And he, very shortly before that, just promoted his dutiful lab assistant to really be like his right-hand man. And because all of these people worked for the kings and queens in their countries, I believe these guys were Dutch, the king and queen of the day and the people who worked under them promoted Johannes Kepler to be the person who took over Brahe's work. And so Kepler now had access to all of this data that he wanted to use to confirm his ideas, later coming to be known as Kepler's laws of planetary motion, and ultimately, as we now know, was correct in a lot of ways. And that data collected by Tycho Brahe, who is often forgotten by history, or at least is not mentioned as much as Kepler, that data was pivotal in terms of his ability to be able to formulate these laws known as Kepler's laws of planetary motion. And so an interesting little bit of luck was really all it took. And I think it's important to realize the reason why I wanted to talk so much about this is because, number one, it's like a weird little interesting historical tidbit, but also because it's very important to realize that Kepler's laws are not theoretical, if you want to put it like that, although that's a little sketchy. It's probably more accurate to say Kepler's laws are really pretty much directly related to observations. It's not something that he just guessed or assumed might be true. They are things that are confirmed by observation of objects that are in orbit around the sun. And so that's an important thing to understand first as we go into this. Now, before we get into Kepler's laws, I want to just very quickly talk about one definition, because Kepler's laws use this term, and obviously if you don't know what this term is, then you're in trouble. And this term is called orbital period, or just period in general. We talked about this in honors physics for sure. We did it in the context of waves, but it's important to realize in whichever context you're talking about, the term period means the same thing. And so what we're going to say here first is that the period is defined as the time taken to complete one cycle of a repeated, which we usually call periodic, motion. And so if we're talking about like a wave, we're talking about the particles vibrating up and down in that repeated pattern. And that's why we talk about the period for wave. For a planet, this would be the time it takes for the planet to complete one orbit. And so it's important to realize orbital motion is periodic motion because it happens regularly and in a repeated pattern. And so I think at this point, it would be important to point out to everybody that if for a planet, like it says in that last sentence there, this would be the time it takes to complete one orbit, then what that means is that for planets in the solar system, we generally refer to the period as a year, right? Because the time it takes for the Earth to go around the sun once is what we call a year, 365 days. And the last thing we'll say just quickly before we move on, because this will come up in an equation not only later in this video, but also like a bunch of different times this year, is that the symbol for period is an uppercase T. And I hope to some degree our usage of the letter T makes sense, because period is in fact a time. And so the fact that it is a time means we're going to want to use a symbol that we usually use for time, but because it's a special time, we don't use the lowercase t, we use the uppercase T. And we should also probably just mention here that the unit is in seconds, at least naturally. Of course, that's just a standard SI unit. This is very important, not only for the things we're going to discuss today, but for the rest of the year. So take a second to pause this video here and write that down. And when you hit play, we'll move on. So I'd like you to write this down under the heading Kepler's laws of planetary motion. There are 3 laws of planetary motion as described by Kepler, and we are going to go through each one individually. And so we'll talk about them generally here first, and then we'll dive into each one specifically. And so the first thing we'll say here is that Kepler's laws of planetary motion describe the motion of planets around the sun. It's important to realize that, like, we know a lot about space now, right? We know that there are all sorts of different objects and, like black holes and all sorts of things like that. They didn't really know about all of these different things, of course, in the late 1500s and early 1600s, because they were using telescopes that were not that powerful. Of course, because there was no light pollution, there were a ton of stars that were visible with the naked eye, but planets, being pretty big reflectors of sunlight, you actually can see with the naked eye. And so, a telescope would be able to give you a pretty good look at these planets. And so these laws describe the motion of planets around the sun. We can actually extend them a little bit to any orbit where something is orbiting another object. But specifically, Kepler's laws were designed to describe the motion of planets around the sun. It's also important to emphasize the point here that Kepler's laws are not perfect. In other words, they're actually slightly incorrect, because they only address the motion of planets due to the gravitational influence of the sun. Now, I want you to take a second to think about that. Why, if Kepler's laws only address the motion of planets due to the gravitational influence of the sun, why would that make Kepler's laws slightly incorrect? Why, if Kepler's laws only address the gravitational influence of the sun, does that make them slightly incorrect? And the basic idea is that the actual path of planets slightly deviate from the paths predicted by Kepler's laws because of the gravitational interactions between the planets themselves. Yes, it is true that Earth's motion is mostly determined by the gravitational force acting on the Earth from the sun. But it's also true that the moon exerts a force on Earth, and Mars exerts a force on Earth, and so do Mercury and Venus and all the other planets, really. And so obviously some of those gravitational forces are bigger and some of them are smaller, and so some matter more and some matter less. And of course, describing all of the objects in orbit in their motion at the same time is an enormously complicated task, because their position varies, because they all take a different time to go around the sun. And so In some cases, you'll have more planets in front of you, or essentially like going in the motion that the Earth is going, and some behind, and so you'll have forces acting in different directions, and how they combine to give you a net force is like super, super, super complicated. You have to use differential equations, really, high order calculus, to be able to describe this in great, great detail. But Kepler's laws, being something that we're going to be able to use only algebra for, is a pretty good way to describe these planets' motion. It's just that it's off a teeny little bit. And you don't have to write this part down, but I do think it is an interesting note that it is true, actually, that these deviations from Kepler's predicted paths actually led scientists to discover Neptune and Pluto. I think the basic idea is people were looking at their data and they said, like, that's weird. Theory predicts this planet should be here, and it's here. It's almost like something back here is pulling it out of its predicted path. And the exact way it's being pulled would kind of suggest that there's something big right here. And then they would point their telescope at that, and they were like, oh my God, that's another huge planet. Not the case for Pluto, obviously, because Pluto is not huge. It's actually really tiny, and no longer a planet, but you get the idea. Take a second to pause this video here and write that down, and when you hit play, we'll get into Kepler's first law. So Kepler's first law is a pretty basic one. That said, I think there is some important stuff to understand about it, and some other important definitions for us to give just while we're on the subject to make sure that everybody really understands it. But it's important to realize 2 of the 3 laws that we're actually talking about, at least for right now, will not be accompanied by an equation. And so when we're discussing these things, we'll be discussing them just basically saying what they are and trying to use that basic understanding to describe the motion of planets. And so Kepler's first law, at first glance, looks really simple. Kepler's first law says the path of each planet is an ellipse with the sun at one focus. That's it. And so if we were to sketch it, it would look like this. And so here we see this elliptical path. From this particular point of view, the planet is orbiting counterclockwise, as you can tell from these arrows here. And the sun is located at one focus of the ellipse. That's pretty much it. Now, of course, this whole point here, like the path of each planet is an ellipse, is usually where people stop reading. But this point about the sun being at one focus is an important thing to understand. And so, obviously, the question is, unless you all remember that from geometry, what is the significance of the focus of an ellipse? And the idea here is pretty simple. If we take any point on the outer edge, or the perimeter of the ellipse, and you draw a line to each focus, the sum of the lengths of those lines is the same. That's what makes the focus the focus. So the plural of focus is foci. The foci are just the points where that is true. And so notice, if we do this from any point, like if we do it from over here, and I think this makes sense, because if we do it from point, let's just call this point Z, this line, which we'll call L3, is really, really, really super short, but then this line is much longer, such that L3 plus L4 is going to be equal to L1 plus L2. That's the basic idea. I think it would probably be important to take a moment to sketch that. So take a moment to sketch that, pause this video here, and when you hit play, we'll talk a little more about ellipses. An ellipse has a bunch of different parts. Now, it's important to recognize this is not a geometry class. I'm not going to test you on these particular things, but it's just good to know in general. An ellipse has two axes, one called the major axis, and I think it's pretty easy to remember here that that's just the long one. So the major axis, like let's just say this is point 1 and this is point 2. The major axis is the length between point 1 and point 2. So the major axis is the long axis. And of course, there's another axis that you can see here. And let's just say this is between points 3 and points 4. That would be the minor axis, and that's just the short axis. I think that makes sense. The major is long, the minor is short. It's easy to remember. And so as you can see here, there is a bunch of labels at the bottom, and they've labeled two parts in particular, the semi-major axis and the semi-minor axis. Think about the usage of the word or the term semi in semicircle. They're talking about only part of the major axis. And so the semi-major axis is just half of the major axis. And the semi-minor axis, which is here, the length of B, as is labeled in this diagram, that would be half the minor axis. And of course, the reason why that is important is because the semi-major axis's length is actually something that is going to come up again and again and again when we do calculations. Before we get to that, though, I'd like you to just sketch some basic details about this diagram. The labeling of these points C, R1, and R2 here has no relevance to this course. So, like, don't worry about them. But I think you should make, like, a basic sketch of this diagram right in the stuff we wrote over here on the right side of the screen. And when you hit play, we'll talk about the significance of the semi-major axis. Okay, so as I mentioned, the semi-major axis is an important measurement. Why? Well, it's because the mean distance from the sun, which, as I think in the context of the gravity equation, you might realize is an important number, is actually just the length of the semi-major axis, which again is half the length of the major axis. Now, let's be clear. You are never going to have to do any sort of like elliptical geometry here. They are never going to give you the length of the major axis, and you're going to have to find half of that and then say that that's the mean distance from the sun. It doesn't matter. But it's important to realize when we have been doing these gravity problems so far, what you have seen in the problems, whether you paid attention to them or not, is that they tell you things like the mean distance from the sun. If we're calculating the gravitational force between the Earth and the sun, we use the mean distance from the sun. And so that's an important thing to realize, that the gravitational force between the Earth and the sun changes all the time. Because in the equation G m1 m2 over r squared, while the masses are constant, or at least relatively constant, right? The sun is converting its mass into energy, but difference is negligible when we're looking at it. While the masses are constant, the distance is always changing. And so the gravitational force is always changing. But what we do to sort of simplify these calculations is we just say, let's just talk about the average gravitational force. And the average gravitational force is computed using the mean distance from the sun. Now, as far as how that actually works in terms of the geometry of the ellipse, is that it's just the length of the semi-major axis. Now, we could prove that out using, the geometry of an ellipse, but we're not going to. This is just a good fact to keep in mind. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, and just very quickly before we move on to the second law, I just want to say two more quick things, which I think is really going to set us up for the next law, and the other times that we'll see this, is that the planets follow elliptical orbits as a consequence of the inverse square law and energy and angular momentum conservation. And so as a result, we're going to keep coming back to this. We're going to come back to this 3 separate times. First, we're going to come back to it in the next unit when we're talking about uniform circular motion. When talking about uniform circular motion, we will actually be able to see how Newton used Kepler's laws and the principles of uniform circular motion to derive his universal law of gravitation. Newton did not guess he didn't just say like, well, maybe it's gm1 m2 over r squared. He came up with it by using Kepler's laws and the principles of uniform circular motion. Then we'll come back to it when we talk about conservation of energy. And then we'll come back to it one last time when we're talking about conservation of angular momentum, which is actually something you've never seen before because it is only in this course and not the honors course. And so we'll be able to look at this from a bunch of different perspectives and really understand why these things are the way they are. Lastly, we'll just say, because I think this is an important thing too, that Kepler's first law says the path of each planet is an ellipse with the sun at one focus. Does that mean that planets cannot experience circular orbits? I think a lot of people think the answer to that question is usually yes, but no, it doesn't mean that. It's important to realize that a circle is just a special case of an ellipse. And so it says here, since a circle is really just a special case of an ellipse, where the 2 foci lie right on top of one another, that should say a circle, circular orbits are possible, but very unlikely in nature. Slight deviations in the orbits caused by interplanetary forces and other effects cause most objects to have an elliptical orbit, though orbits for planets in the solar system have a very small eccentricity. Now, if you don't remember from earth science or geometry, or never took earth science and don't remember from geometry, the eccentricity basically is a measurement of how elliptical an ellipse is. And so a circle has an eccentricity of 0. So the higher the eccentricity is, the more elliptical it is. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so let's just take a quick look at some of these orbits. Here are the elliptical orbits in the solar system as described by Kepler. So as you can see here with the sun at the center, we have each planet's orbit shown in the diagram. Now, if it isn't any surprise, Pluto's looking weird. In a game of which one of these is not like the other, the answer is definitely Pluto. Notice Pluto is not a planet anymore. It crosses the orbit of Neptune twice. But you can see here that Pluto's orbit has a pretty high eccentricity compared to the other planets in the solar system. And so, as it turns out, for Earth, Mars, and Venus, their orbits are actually fairly circular, although this diagram kind of makes them look flatter than they actually are. As you can see, the asteroid belt is also fairly elliptical, and then we get sort of more and more smushed, a longer major axis and a smaller minor axis as we get further and further out from the sun. To look at it in a slightly different way here now with eccentricity values, you can see there in this is a much better representation of the shape. Venus has a super small eccentricity. The orbit really is very close to being circular. Earth's is pretty small too, and then we get up higher as we go into Mars, and then these other 2 objects, Icarus, which is an asteroid, and Halley's Comet, which I'm sure you've heard of before. Halley's Comet comes around the Earth once every, I think it's 73 years. Don't quote me on that. You are all sitting at a computer right now. You can look that up. I think it's 70 something years, something like that. It's a while. And so that makes sense. I think that it doesn't come by Earth very often because, as you can see here, the orbit is, number one, huge. Can't even be shown on this picture here. And number two, pretty darn elliptical. And so once it passes by, it's got a whole way to go around. If you just imagine in your mind's eye here how much farther this thing goes off the screen to complete the entire ellipse. And so that's Kepler's first law. Now we can show a video here which basically represents to you how this has consequence in nature. So as you can see here, these are the planets orbiting Sun, and they're moving in ellipses. That's really all this one says. The Sun is at the focus of the ellipse. That's the basic idea. And that brings us to Kepler's second law. Kepler's second law, conceptually speaking, I think, is the most complicated. Let's take a look at it and then we'll ask some questions about it. Kepler's second law says each planet moves so that an imaginary line drawn from the planet to the Sun sweeps out equal areas in equal times. The obvious question here is, what? It'll probably be a little easier to understand when looking at a diagram. Essentially what we're saying is that this planet moves along that ellipse shown by that dotted line. When it travels from A to B in this diagram, if you drew a line between the planet and the Sun, as this thing moved from A to B, there would be an area swept out as the object moved from A to B. When we say swept out, it basically just means this area is created, right? Because when the object is just at A, the line between the Earth and the Sun, or the planet and the Sun, is just a line. But when it moves from A to B, it sort of drags out an area. The area gets bigger and bigger as the object, the planet here, moves from A to B. Essentially what it's saying is anywhere along this ellipse, when it moves between 2 points, in equal amounts of time, no matter what, the areas are going to be equal. And so this thing, in a certain amount of time, is going to sweep out an area. In the same amount of time as this thing moves from C to D, this thing is going to sweep out another area. And what Kepler's second law says is that those areas are equal. Now, a pretty good question, I think, would be, how do we know that that's true? And the answer is quite simple. We know that that's true because of angular momentum conservation. So as I mentioned, we are going to come back to this when we talk about angular momentum conservation, and we're actually going to derive Kepler's second law using angular momentum conservation. And so you will see this in the future in more detail, I think. But this is essentially what Kepler's second law is saying. And like I said, despite the fact that we don't really have the understanding, because you've never seen conservation of angular momentum before, we don't really have the understanding to be able to sort of like fully describe Kepler's second law. I think it still points out a really important concept about planetary motion. And so I'd like you to take a second to pause this video here and write that down, draw this diagram, because I'm going to flip to another slide here and I'm going to ask you to think about some things with this diagram here that I think will allow you to see the important physics concept for yourself. So take a second to pause this video here, write down that definition, write down that diagram, and when you hit play, we'll investigate this a little more. So let's ask some questions here. The first question is a pretty basic question. How can we describe the condition of the motion that must be satisfied in order for this to be the case? What has to happen with the planet in moving from A to B compared to it moving from C to D in equal amounts of time for this to be true? Take a second to think about that here. Look at the diagram we just drew and see how the planet moves from A to B, and then look at it from C to D. And what we are saying is those areas are equal and those times are equal. What does that tell you about the planet? What it tells you about the planet is that in order for these areas to be equal in equal times, emphasis on in equal times, the planet must move faster when it is moving around the sun, closer to the sun, and slower when it's further away from the sun. Now, I'm going to come back to this here in a second, but I just want to go back to this diagram to make the point. Look at how tiny this distance is. This is a small displacement. This is a big displacement. Delta x2 is bigger than delta x1. But t2 is equal to t1. And since v is d over t, or delta x over t, it's got to go faster between point C and point D than it is between point A and point B. And I think that makes a lot of sense based on not just conservation of angular momentum, because if you knew conservation of angular momentum, it would make a hell of a lot of sense. But I think it makes a lot of sense in terms of the physics principles that we've already discussed so far this year. Why does it make sense that the planet is going faster between C and D than it is between points A and B? What's the difference? The difference is how close it is to the sun. Since the gravitational force is inversely proportional to the separation distance, the square of the separation distance, the closer the planet is to the sun, the larger the gravitational force, the higher the acceleration, and thus the faster the speed. On the other hand, when the planet is further away from the sun, the force of gravity will be smaller, so the acceleration acting on the object will be smaller. Coupled with the fact that at some points the acceleration is going to be directed opposite the direction of the velocity, it's going to result in the object moving with a smaller speed. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So just to tie this up here, to wrap it up in a nice, neat bow, we'll say here, it's important to recognize, like, let's look at the planet as it's moving from D to A. Basically, this whole time, after this point here, the gravitational force has a component that acts in the opposite direction of the planet's velocity. And so the whole time it's moving between D and A, at least after this point, it's decelerating. It's getting slower and slower and slower. And then notice this point is relevant because as the object moves really from between A and B all the way back to C, this whole time, the sun has a component of its force, like here. The sun has a component of its force which is in the direction of the motion. And so it's making it speed up and speed up and speed up. Now we can look at that in a nice animation that I have here, which I think really kind of drives the point home. So notice, as it gets farther away from the sun, it's moving slower and slower and slower. As it gets closer to the sun, it's going faster and faster and faster. And what Kepler's second law is saying is the area of all of these shapes, which are just being drawn and then stopped drawn in equal amounts of time, those areas happen to be the same. So notice the triangles, so to speak, they're basically almost triangles. They get skinnier and longer as you get farther away from the sun, and they get shorter and fatter as you get closer to the sun. And these areas are always equal, is the point here. And so that's an important thing to realize. The key thing that you need to understand about Kepler's second law is that it dictates essentially how the planet moves. It moves faster when it's closer to the sun, and it moves slower when it's farther away from the sun. And we can doubly justify that by talking about Newton's universal law of gravitation, because notice here it's getting slower and slower and slower because gravity's pulling opposite, and then here it's getting faster and faster and faster because gravity's pulling in the same direction. And it's sort of like slingshots around the back end of the sun over here on the right because of that huge gravitational force causing a huge gravitational acceleration. And it's important to recognize also, not only is the Earth getting faster because it's moving in a direction that forces the gravitational force from the sun to act in the direction of its velocity, it's also getting faster because it's getting closer to the sun. And so that force, which is acting in the direction of the velocity, is actually getting larger and larger and larger and larger. That's a key detail which is not to be missed also. Over here, on the other side, when it comes around, it's also important to realize that here, yeah, it's being decelerated by the sun, but it doesn't slow down to a stop or anything, because as it gets farther away from the sun, it gets the gravitational force from the sun gets weaker and weaker and weaker. And with that, that's really it for Kepler's second law. The only one, obviously, that we have to discuss is Kepler's third law. As I mentioned in the beginning, there are 3 of Kepler's laws of planetary motion, and Kepler's third law is the only law with an equation. And so, because this video is already getting a little long, we'll leave it at the first 2 laws for today. Tomorrow, we will look specifically at Kepler's third law and use it to do some calculations. All right, everybody. Have a good one.